Okay guys, so this is the bromination of phenol versus benzene. And I'm going to kind of build up to the final answer of why phenol brominates a lot more easily, or a lot more readily than benzene does. But it's going to take me just a few minutes to kind of build up to that answer. So do bear with me, that is the answer I'm getting to, it just might take a while. So to start off with, I'm going to talk about how cyclohexene will brominate. And what happens is in cyclohexene we have this double bond. And because of this double bond, we have 4 electrons in a very small area of space. A single bond would be 2 electrons, so a double bond would be 4. So that's a lot of electrons. We would say that is a high electron density. And because we have a high electron density, as this bromine approaches the double bond, the electron density here is going to repel the electrons in this bond. So my electrons are going to get pushed back towards this bromine here. And what that's going to do is it's going to induce a dipole. So as the electrons are now closer to this bromine, this will get a negative dipole, and as they're further away from this one, we will have a positive dipole. And because my cyclohexene has induced a dipole, it can now attack it and a reaction can happen. So if you think back to the first module of AS chemistry, double bond's going to attack here, this bond's going to break, and so on and so on and so on. Now, there's something different in benzene. In benzene, we don't have 4 electrons in the same space, because if you remember, all of the carbon's p orbitals overlap to form that delocalized electron ring. So I've got my 6 electrons, 1 from each carbon, not localized in any space, they're all spread out. And what this means is, and this is the key thing, we have a low electron density. As my electrons are spread out and they're not all in one spot, we have a low electron density, so this will not be able to induce a very big dipole in the bromine. As my bromine approaches, as there's not that many electrons, yes, the electrons here might get pushed away a little bit, but not very much. So my dipole will be tiny. And because of that, we will not be able to initiate the reaction. The electrons here will not be attracted to this bromine sufficiently to start the reaction. Whereas here, because we have a positive dipole, the electrons are sufficiently attracted, and that's what starts the reaction off. So I guess the key thing to remember from this is the reason benzene does not brominate easily is because benzene has a low electron density. So because of this, when we brominate benzene, we only get 1 Br added at a time. You end up with bromobenzene. You wouldn't end up with tribromo, just 1. We need to heat it to make this reaction happen, and we need to use a halogen carrier. If I was adding bromine, I could use AlBr3 or FeBr3. Okay, so a halogen carrier. Let's have a look at phenol now. So when I brominate phenol, what happens is it brominates 3 times. We get 3 bromines added. Okay. Also, we don't need to heat it when we do this. So this can be done at room temperature. And we do not need a halogen carrier. It just does it. If you used to take some bromine at room temperature, some bromine water, and you used to add it to some phenol, it would just instantly go really quickly. It really is readily brominated. So what's going to happen here, just to kind of explain what I'm about to do, I'm going to add on my hydrogens here, just to show you what's happening. If you was to do this in an exam, you don't need to draw the hydrogens on. I'm just adding them on to show you what's happening. So I've got my hydrogens here, and I've got my 3 Brs. Let's just draw them out like this. So Br to Br, Br to Br, and Br to Br. And what's going to happen is, here's my phenol. We get triple bromination, and it's always on carbons number 2, 4, and 6. So that's carbon number 1, so 2, 4, and 6. And you can see, to add these 3 bromines on, I must have removed these 3 hydrogens. So these 3 bromines here get added on. The 3 hydrogens I've taken off here, which have been replaced by the bromines, they add on there. So what I end up with, let's just get this back to normal. So what I end up with is my 2,4,6 tribromophenol and 3 HBr. Okay, these H's come from the replaced H's here, which the Br's swapped for. So that's what happens. Now let's talk about why that happens. Why is it that phenol is brominated so much more easily than benzene? And you've probably guessed it, it's all about this OH group. So if I draw out, I'll draw a skeletal formula. Now, if you don't know about the delocalized electron ring system in benzene, I have got a video on that, so definitely stop this now and watch that first, because you need to know about that ring system before you can understand this. So if you do understand that, you'll know that the 6 p orbitals of these 6 carbons here all overlap to form this delocalized electron ring system, and that's above and below the plane of the carbons. This is why phenol brominates more easily than benzene, because phenol has an oxygen, and this oxygen has got 2 lone pairs of electrons. Now one of those lone pairs is going to be in a p orbital, and this p orbital lines up with this delocalized electron ring perfectly. So what it can do, just like the 6 p orbitals of these carbons, the p orbital of my oxygen can also overlap with this ring. And that forms something called an extended delocalized electron ring system. Bit of a mouthful, try saying that 5 times fast. So we have now made an extended delocalized electron ring system by oxygen overlapping its p orbital, or one of its p orbitals, with my delocalized electron ring in the benzene. So that's step 1. That's like the first part of my answer. The oxygen overlaps one of its p orbitals with a delocalized electron ring. Once it's done that, the oxygen can donate the lone pair of electrons in its p orbital to the delocalized electron ring. So this oxygen is adding more electrons to this delocalized ring. But if you're adding more electrons to this ring, think about what that's going to do to the electron density. Well, it's going to make it higher, isn't it? So before I added this oxygen, each of these carbons had donated 1 electron to the ring. So that was a total of 6 electrons. After my oxygen overlaps its p orbital and donates its lone pair to the ring, we've added 2 more, so we've now got 8 electrons. That's like a third again, higher. So that's a lot more electron density. And what that means is we have enough electron density, this is sufficiently electron dense to induce a big enough dipole in the bromine to start the reaction off. So I guess ultimately your final answer for why phenol brominates more readily is because in phenol the electron density of your ring is large enough to induce a dipole in the bromine. Whereas in benzene, it's not, because you don't have as many electrons in this ring. Okay? And that is the bromination of phenol compared to benzene. Definitely, you're going to want to remember these 3 differences as well, because not only do they ask you why this brominates more readily, they'll ask you to talk about the differences in bromination as well.